Welcome back, students. Let's pick up where we left off and balance some equations. I'm going to go ahead and start you off with this one, and I'm going to use the process that we did before where we found our reaction arrow that splits our reactants from our products. So on the left-hand side is our starting, right? This is the start, and over here is our end. And we need the same number of atoms of each type on both sides. So we can go ahead and start by taking stock. We have 1 aluminum on this side and 3 bromines and 1 potassium. Just to make my life easier and yours too, I'm going to take this order that I wrote, my aluminum, bromine, and potassium, and I'm going to use that order on the next side so that I have less stuff to have my eyeballs focus on. So I have 1 aluminum on this side, 1 bromine on this side, and 1 potassium. What this helps me see is that I do not have the same number of bromines. So let's start with bromine. In order to get 3 bromines on the product side, which is the end, I need to put a 3 coefficient in front. Remember, all I'm allowed to do is add coefficients. I cannot change chemical formulas. Once I put the 3 in front of there, not only does it change my number of bromines to 3, but it also changes my number of potassiums to 3. Well, that messed up my number of potassiums because now I have 3 in comparison to 1, so I need to remedy that. Therefore, I'm going to put a 3 in front of potassium to make sure that I have the same number of potassiums on both sides. And let's just double check that my aluminums are still good. I've got 1 aluminum here and 1 aluminum here. Great. Now I can do 2 double checks. 1, just look through, make sure I have the right number of atoms on both sides, and 2, make sure that I have the lowest whole number ratio. And I do, because there's an invisible 1 here and here that you can either choose to put in or not put in. Let's do another example. In this equation, I'm going to do the same thing, split my left and my right. I've got 1 iron, 1 sulfur, 1 hydrogen, and 1 chlorine. Now, just to make it easier on myself, I'm going to list all of the atoms that I just listed on the product side in the same order, even though they're not in the same order in the chemical equation. So I have 1 iron and 1 sulfur. I have 2 hydrogens and 2 chlorines. This helps me recognize that I have disagreeing numbers of hydrogen and chlorine. Does it matter which one you start with? No, pick one. All right, I'm going to pick chlorine. Why? Because I like it. So I have 2 chlorines on this side, and that means I need to put a 2 in front of HCl so that I can get 2 chlorines on the reactant side. Well, when we do that, it also changes the number of hydrogens, so that changes my number of hydrogens to 2. Let's look at our number of hydrogens on the product side, and would you look at that? It's 2 as well. I'm going to put a smiley face there because I'm so happy. So now I just double check my irons and my sulfurs, and they're the same on both sides, and I'm done. You go ahead and give this one a try. Now, instead of you looking at A, B, and C and deciding if they were balanced, what I did was I really quickly balanced this equation, and then I can just compare what I got to the answer, and I am choosing C. Let's talk about how I got this equation balanced really fast. Yes, you can do the splitting method where you list out all of your atoms on both sides. Personally, I don't do that. I have a little bit more practice, and so I'm more comfortable with doing a way that's in my head. I want to show you the way that I do in my head. So in order to do that, I'm going to erase these and then start from scratch. What I see right away when I look at a balanced equation, or I guess what I look for, is not having the same atoms on both sides. So I just pick an atom. Right away, my eyeball sees that I have 2 bromines here and only 1 bromine here. So I just focus on that element first. In order to remedy the fact that I have 2 bromines on the reactant side and only 1 bromine on the product side, I put a 2 coefficient in front of sodium bromide. But then I recognize that that 2 distributes through to the Na and to the Br. And so I need to go and double check my sodiums on the other side. I have 2 sodiums on the product side. Now I go to the reactant side. I only have 1 sodium. So I need to fix that by putting a 2 out in front. Then I look at my sodiums and say, hey, that 2 distributes through to my sodiums, but also to my fluorines. So even though my sodiums are perfect now, my fluorines just went from 1 to 2. So let's double check on the product side. So now I have 2 fluorines on the reactant side. And would you look at that, smiley face, you have 2 fluorines on the product side. Personally, I like this way better. I feel like it takes less time because I don't have to write everything out. But some students don't feel comfortable with it yet. So you use the logic that's going to work for you. Let's take it up a level in difficulty. What we're going to do in this equation is we are going to start pulling in polyatomic ions. Those darn pesky polyatomic ions are not going anywhere, so make sure that you still know them. One of the things that I want to point out is that on the left-hand side of my reaction and on the right-hand side, I have sulfate. Instead of breaking this up into sulfur and oxygen, because you have sulfate on the left and sulfate on the right, just treat it like it is one entity. So when you're making your list and you're splitting your left-hand side from your right-hand side and you're saying I have 1 copper, go ahead and also say you have 1 sulfate and that you have 1 aluminum. Then on the product side, you have 2 aluminum. Remember, this 2 means you have 2 of the thing before it. This 3 means you have 3 sulfates. So I have 3 SO4s and I have 1 copper. Notice here how I forgot, because I was so focused on sulfate, to make sure that my list on the product side matched the order on the reactant side. It doesn't really matter, it just makes it easier. So if you want to switch them around, go for it. If you're happy with this, that's fine. So now I can look at this and say, all right, my sulfates are out of whack and my aluminums are out of whack. Out of whack meaning there's not the same of each on both sides. Pick whichever one you want to start with. It doesn't matter. So let's, pick the sulfates. So I'll pick the sulfates. I've got 3 on the product side. I need 3 on the reactant side. Now that I have 3 sulfates here, because remember the 3 goes to the copper and to the sulfate, that messed up my number of coppers. So I got to put a 3 here. Oh, well, now I have aluminums and coppers that are not agreeing with each other. And again, it doesn't matter which one you do next. Let's just do coppers to get rid of that. Cross that off our list. Okay, so our copper is all set now. Finally, we can look at our aluminum. In order to get another aluminum on the left-hand side, we just put a 2 in front of here because that means I have 2 aluminums, and my aluminums now check out where they have the same number on both sides. So I can go through my double check, making sure that I have the same number of atoms on each side of the reaction, right? The left-hand side, the reactant side, and the right-hand side, which is the products. And then I can check again to make sure that I have the smallest whole number ratio. Now, this next one is a little bit harder. I've already taken stock of my different elements. So let's split up our left-hand and our right-hand side. Notice how in this, I had 2 places where hydrogen existed. And I had an error. That's better. So I have these 2 different places that hydrogen exists, and that makes this really hard because, like in our last example, there is a polyatomic ion. I have OH hydroxide, but there's no OH over here on the product side. There's H2O, which is similar, but not the same. So these can be really tricky. I'm going to show you how you might want to do them initially, and then I'll show you how my brain does them. So I took stock of all of my atoms, and I like to suggest to students to worry about the hydrogen and the oxygen last. So let's focus in first on the fact that we have 2 bromines on one side and only 1 on the other. So let's go ahead and put a 2 in front of here. When we put a 2 in front of here, that 2, remember, it doesn't just distribute to the bromine, it also goes to the hydrogen. So I now have an additional hydrogen. I have 2 coming from the HBr, and I have 2 coming from the magnesium hydroxide, so a total of 4. So our magnesiums are perfect. Let's focus in on the hydrogen and the oxygen now. So what's happening over here is I have 4 hydrogen and 2 oxygen. And over here I have 2 hydrogen and 1 oxygen. So what I see is that if I put a 2 in front of H2O, then that doubles this. That's exactly what I want. So now I'm done. But students still feel a little shaky with this one, so I want to show you how I think about it. When I work through these, what I like to do, and you might not be ready for this, and that's fine, right? If you don't like what I'm about to show you, then you revert back to what I showed you previously. So here's the difference. I like to look at my H2O as if it is HOH. Because if I mentally look at H2O as if it's HOH, then I have a polyatomic ion and a polyatomic ion. And to me, that makes it easier because I can go through the same process, see that I have 2 bromines, so I need a 2 in front of here. And then what I see is that I have 2 H's and 2 OH's. Well, if this is made up of H and OH, then if I have 2 H's and 2 OH's, that means I need 2 waters. So that's how I like to do it. You need to do what works for you. Why don't you go ahead and take a moment here, look at this one, and see if you can balance it. What I did when I went through this one is I noticed right away that I had 2 nitrates, so I knew I had to put a 2 in front of my lithium nitrate. That messes up your number of lithiums, so I need to put a 2 in front of lithium bromide. That means that I have 2 bromines, and would you look at that? I've got 2 bromines. And then I double check my calciums. So that's how you do it when you end up getting comfortable enough not to have to make the list. You might never get to the point where you feel comfortable enough not to make the list, and that's fine. You just need to do what works for your brain. Now let's work on our final example. In this example, I've already taken stock of my different atoms. This one is really a difficult one, so I'm going to lead you through some of the logic, and you might feel like we're long and meandering through the logic, but I want to show you what it's like in real life when you get stuck. So the first thing that I notice here is we don't have any of the same number of atoms, like none of them. So the other thing that I notice is on one side, on the reactant side, I've got 2 oxygens, but on the product side, I have 3 oxygens. Whenever you have an odd number on one side and an even number on the other side, that's going to give you trouble. So one of the nice ways to start is to start thinking about how to make that oxygen that's on the product side that's odd into something that's even. And when we start making that into something that's even, we have to multiply it by an even number, right? So an odd times an even is going to be an even. So the other thing I notice is I have 6 hydrogens, and on the other side I have 2 hydrogens. So if I want to fix my number of hydrogens, I would need to put a 3 in front of here, but 3 is not an even number. So what I probably need to do is double that. Now you could, I'm going to show you, you know what, I'm not going to double it yet. I'm going to show you if a student didn't know about the even and odd stuff. So let's put a 3 there. We put a 3 there. We change this into a 6. That takes 3 times your oxygens, which is 3, plus these 2 makes this into a 5. Now we've fixed our hydrogens, but our oxygens are still off. Now let's fix our carbons. We've got 2 here, we have 1 here. We'll put a 2 in front of our CO2. When we do this, now we have 2 times 2 plus 3 times 1. So we have 4 plus 3, 7. And we still don't have the right number of oxygens. Now, if you get to this point and you're thinking, I can make that 2 oxygen into a 7 if I could use a fraction. If you end up with a fraction here, let's do 3.5, right? Would that work? Is that what a student would want to do? 3.5 times 2 is 7. Okay. So this is probably what I think a student would naturally come up with. And if we got to this point and you see that you don't have whole numbers, then what you're capable of doing is doubling everything. What that means is you need 2 CH2H6. I'm sorry, C2H6. 7 O2. 4 CO2. And 6 H2O. Part of the reason these ones are hard, and these are combustion reactions are always the toughest to balance. They just get really big coefficients, and I think that freaks people out. But also that idea of having an odd number of oxygens really throws us. So this is what you should get. And I can lead you through the logic that I would typically use, because what I showed you here was not the logic that I would use. So let me show you my logic. So for my logic, what I would notice is that because I have 6 hydrogens here and only 2 hydrogens here, and the fact that I have an odd number of oxygens, if I tried to figure out how many H2Os I would need 3 of them in order to get the right number of hydrogens. But really, I also need to have an even number of oxygens. 3 times 1 is still 3. So in order to make this an even number of oxygens, I would put a 6 here. That gets me 12 hydrogens, which is totally not what I wanted. And so that means I have to double this. Well, that messes up my number of carbons. So then I have to come in and put a 4 right here. Now I'm going to add up all the oxygens I have on my product side. So I have 4 times 2, which is 8, and 6 times 1, which is 6. And notice that I have 14 oxygens. In order to get 14 oxygens over here, I need a 7. I still come up with the same answer, but my logic might be different than your logic. And that's fine. You'll get to a point where you start to feel comfortable after you've done enough problems. One last thing before we wrap this up. When you start seeing chemical reactions, you're going to start seeing these solid liquids and gases after them. So if you see S, that's for solid. If you see L, that's for liquid. If you see G, that's for gas. And if you see AQ, that's for aqueous or aqueous, depending upon your pronunciation, which is a fancy chemistry way of saying dissolved in water. So I don't want you to be freaked out with those yet. We're not going to work with them at right this moment, but we will work with them later on in this chapter. So just be aware that those are there and they have no impact on how you balance your chemical reaction. Let's wrap up. In this video, we went through chemical equations, looking at the different format of chemical equations and how the left-hand side is your reactants, the right-hand side is your products. We utilized the law of conservation of mass in order to lead us into why we have to balance chemical equations. And then we made sure we understood the difference between coefficients and subscripts within balanced chemical equations. Then we worked to balance some equations. We did it in pictures. We tried to really make sure that people understood that it has to be the smallest whole number ratio. We talked about how some elements are diatomic and that we shouldn't be scared off by phase notations. Balancing chemical equations can be challenging, so go ahead and make sure you give it plenty of practice. Thanks so much. This is Katoni signing out.